Okay, this is going to be my introduction to magnets, or more specifically, magnetic fields that are produced by magnets. Okay, so first of all, let's be aware of the symbol for magnetic field. It's a capital B. It stands for magnetic field, or more precisely, it stands for magnetic field strength. Okay, it's also a vector quantity, and it also can indicate the direction of a magnetic field, but we'll get to that in a moment. Okay, so just be aware of that symbol and what it means, because you'll see it in diagrams and you'll see it in equations. All right, now let's talk about the strength of a magnetic field. It's strongest inside of the magnet and at the poles. And this diagram of the field shows us that. Wherever the field is the most dense, that's where you're going to see the strongest magnetic field. So what do I mean by density? Well, by density, I just mean wherever those field lines are closest together is where you're going to see the strongest field. So you see the field is very strong inside of the magnet, where these field lines are very tightly packed. They're really dense. And then outside of the magnet, you're going to see the strongest magnetic field at the poles, near the North Pole and near the South Pole, where those lines are very close together. Those field lines are very close together. And that's how we interpret those field lines to tell us about the strength of the field. Okay, and another thing that these lines are telling us about is the direction of the field. And the direction is simply shown to us by the arrows. And let's dive into that a little bit. Outside of the magnet, you can see the direction goes from the North Pole to the South Pole. It points away from the north, and then it loops around and goes into the south. But inside of a magnet, we see that the direction is different. It continues through the South Pole and goes right back to the North Pole. And what we get here are what we call closed loops. And this is actually something that's unique to the magnetic field, these closed loops. All right. So let's compare this for a moment to an electric field. An electric field also has strength at different locations. The strength changes. We know that near a positive charge like this, where the field lines are very dense, we have a strong electric field. So that's very similar to the magnetic field. And then as we get further away from the charge, the field lines are less dense in regions like this in green, where the field lines are further apart. You can see that the field and any forces from that field are getting weaker. Okay, so on our bar magnet diagram, we see that the field is strong, like locations near the South Pole, and it's going to be weak out here where the field lines are further apart. And that's how we interpret diagrams like this. But one thing you're going to see that's different about the magnetic versus the electric field is that the electric field just goes out infinitely, outward. But the bar magnet's field, its lines actually don't all go out to infinity. They form these closed loops. And that has to do with the direction. And one thing that's unique about magnets and magnetic fields is with magnets, you always have a north and a south pole. You always have these closed loops. This is called a monopole because it has two poles. But with charges, you can just have a monopole, just one positive or one negative charge. While as a bar magnet, you can have a dipole. You always have a dipole, a north and a south pole. We've never observed just a north or a south pole by itself in nature. And that's one of the things that's unique about magnetic fields. It's different than gravitational or electric fields because it forms those closed loops and you always have a dipole. All right, there's one more really important idea with magnets and magnetic fields, and it has something to do with what happens when you put a magnet near another magnet. So a compass, if you watched our videos for yesterday, you learned that a compass is just another magnet. So consider a magnet that is free to move, like a compass. A compass needle is just a magnet that's been set on a pivot so that it can spin around easily. All right, so the key idea is simply when you put a magnet, like the needle of a compass, within a magnetic field, it will align with the field. It will align with the direction of the field. And this is how compasses work. This is how compasses tell us where the magnetic north and south poles are. Here's a little demonstration. Here's a magnet, and I have a little compass here, and you can see the direction of the field is shown by all these little tiny magnets, and they'll change when I move my magnet around. But my compass, or what I like to call my magnetic field detector, will just align with the direction of the field no matter where I put it. It will align with the direction of the littler compasses in the background, and it'll tell me the direction of the field. So sometimes I call a compass really a magnetic field detector, because that's really what it does, is it detects the direction of the magnetic field. And everywhere I put it, it aligns with the direction of the field. So that is the really a really important concept with magnets and magnetic fields. Okay, I hope this video has been useful, and I hope y'all enjoy the next one.